Thank you, Vipin, for the wonderful overview and introduction to this workshop. And welcome everyone to the opening session of the workshop on foundations and frontiers of generative AI in science and engineering. I'm Anuj Karpatne. I'm from Virginia Tech, and I have the pleasure of co-presenting this opening session along with Aryan Deshwal from University of Minnesota and Jana Dofa from Washington State University. And all the slides that we will be going through have been collaboratively prepared over a series of sessions spanning several months with heavy contributions from Vipin Kumar. So the goal of this opening session is to, as Vipin mentioned, talk about the backward and the forward directions, right? To understand what is Gen AI, what are the different variations of Gen AI methods, what are their different origins, their emerging capabilities, their opportunities, and how they are impacting and are being influenced by problems in science and engineering. Um, for the next 90 minutes, we'll be going in and out in subsets, covering different topics of Gen AI. And we'll take breaks in the middle to stop for the questions. So there are three parts to this opening session. Part one is going to focus on introduction to Gen AI. Part two is going to talk about emerging opportunities at the intersection of Gen AI and reinforcement learning. And part three will talk about opportunities in advancing Gen AI inspired by the needs in scientific problems. So with that, I can move ahead to the first part of the session, which is on introduction to Gen AI models from the perspective of their origins, how they have been enabled by advances in deep learning, what are their differentiating characteristics, what are their emerging capabilities, right? And this is a talk that will be co-presented with Aryan. So we can start with a primary definition, right? What is Gen AI, right? So at a very high level, we can think of the goal of generative modeling to build a distribution of data samples by learning this probability distribution P of X, where X are the data samples, and we would generally assume that X is high dimensional. For example, we are working in the space of generating images, text, code, and so on. Optionally, we may also have information about some conditioning variables Y, in which case we are interested in modeling the joint distribution of P, X, comma, Y. And in the modern era of generative AI, right, you have many different models that are out there, right, which are some listed over there. This is certainly not exhaustive. There are many others, but we'll work with this set. And in this talk, we'll go into more technical details of their origins and their differentiating capabilities. But before we do that, let's talk about what are the different applications of Gen AI. So the most standard or the most mainstream applications of Gen AI is generating text, generating images, generating code, right? Applications that have been enabled by models like ChatGPT and other frontier foundation models. But in science and engineering applications, generative models can be used for many other applications, for many other use cases. For example, generating new molecules, generating new drugs, generating new materials, polymers. Right? Generative models have the capability to perform what-if scenario analysis. Right? What if we change the input forcings? How would it affect changes in the target variables? Or it can even help us generalize to novel unseen tasks, right? Which we'll get to very soon. And you can contrast these applications, these definitions from predictive or discriminative AI frameworks, where the goal is slightly different, where given some inputs, X, we want to predict target variables or response variables y. Right? Y could be categorical, y could be numeric, it could be structured as well. Right? Here we are mostly after learning the conditional probability, right? P of y given x. And there is an entire suite of models that have been developed, ranging from decision trees to neural network models. And this is an area which has seen the most interest, especially in the early phases of deep learning. Right? They enable completely different applications. Right? We can classify objects in images. We can classify the sentiment in text. Right? Or in science, we can predict molecular properties, land covers. Right? And you can see how they contrast with the capabilities that Gen AI models are enabling, right? Where we are not just making predictions on these data points, we are generating these data points. And historically, there has been a lot of contention between generative and discriminative models, right? Going to discussions comparing logistic regression models and Bayesian networks. Um, in the classical frameworks of generative AI, the model structures were handcrafted or were assumed to be known, right? For example, in Bayesian networks. But in the modern era of generative models that we are seeing over here, listed as boxes, we are seeing a few key differences from classical generative models. The first major difference is that instead of using handcrafted or, or structures that are known a priori, we are letting the data drive the learning of these model structures. Right? So these are much more flexible than their historical counterparts. The second key difference is that this distinction between discriminative versus generative models has become quite blurred. Many of these generative models exploit discriminative objectives, discriminative architectures, right? But use them in novel ways to solve generative problems. Another key feature of modern Gen AI models is they exploit some form of structure in the data. For example, the structure of space, the structure of sequences in text data. They exploit some form of regularity or continuity, right? And these three properties, these key differences, would keep on showing up in more detail as we discuss these models going forward. But all these developments that you're seeing in the middle box, right, haven't happened in vacuum. Right? They have been inspired by and enabled by developments that have happened across different research areas or schools of thoughts. Right? These can be viewed as the headwaters, right, that are leading to the river that is now generative AI. And this has been a highly non-linear journey, right, where these models have been inspired by developments from multiple origin pieces. Let's go through a few of these origin pieces in detail to understand where we are coming from. So if a major field that has contributed to modern Gen AI approaches is, of course, Bayesian formulations, which have classical roots in directed and undirected graphical models. As I mentioned, the structures that they're using to model the probability distributions are handcrafted or are known. Right? And these have inspired methods, modern Gen AI methods, such as VAEs, variational autoencoders, that employ similar probabilistic formulations. But there is a completely different area of research that has also contributed to Gen AI methods, which is this entire space of autoregressive models, right, that use some portion of your data to predict the next portion. This can be rolled over in along the temporal dimension, tracing its roots in time series forecasting models like ARMA and ARIMA that are also autoregressive, to Bayesian formulations like hidden Markov models, to sequence-based models like LSTMs, RNNs, and more recently transformers. Right? And we also have autoregressive models going in space, right, where we take a portion of a spatial data and make predictions in the spatial directions, looking at spatial autoregressive models, Markov random fields, and so on. Right? These ideas are now living in modern generative AI architectures like GPTs, right? That would factorize the joint probability distribution that we are after as a product of conditionals using the chain rule. Another area that has contributed to Gen AI is this framework of generative adversarial networks, right? That is inspired by adversarial optimization, where you have a generator and a discriminator that are pitted against each other, and they're both being trained jointly. We also have Nobel Prize winning methods such as restricted bolt span machines, RBMs, that have inspired recent advances in Gen AI that go after the problem of modeling energy functions, right, which can be viewed as unnormalized probability distributions, right? So rather than looking at exact probability learning, can we learn energies? And these ideas now live in score-based interpretations of modern Gen AI methods, such as diffusion models. And in the later part of this talk, we'll go into more details about each of these models. But at this stage, we are just covering the conceptual roots. Another conceptual root of modern Gen AI models is this entire space of latent space modeling, right? Where we assume that the data lies on a lower dimensional manifold, right? Borrowing ideas from linear techniques such as PCA to nonlinear methods such as autoencoder. And they have inspired techniques that now live in variation autoencoders. And finally, we have this area of research in science on forward inverse modeling, right? Where the forward problem is to map some inputs to observed outputs, right? And the inverse problem is then to retrieve the inputs given the observations. Problems such as denoising, compressed sensing would fall in this category, right? And they have influenced advances like diffusion models, normalizing flows, in using very different architectures. So this just summarizes the different conceptual roots, right? The origins that have led to modern Gen AI models. And each conceptual root has its own trajectory of how they have influenced modern Gen AI frameworks. But progress in each of these trajectories would not have been possible, or would have happened at a very slow speed if it was not for key advances in the field of deep learning that have almost supercharged or turbocharged this entire Gen AI revolution. These are listed here in blue. They are representation learning, self-supervised learning, context-sensitive learning, or the use of transformers. And their use is all-encompassing. So they cut across all the modern Gen AI frameworks that are listed over here. So let's go through each of these advances and the historical timeline of advances, of developments in each advance one by one. So one of the key enablers of Gen AI is this idea of representation learning, right? Which is central to the entire field of deep learning, right? Where the idea is to automatically extract features from raw data, from raw signals, as abstract representations in the hidden layers of a neural network. Right? This is different from using handcrafted features that had been the workforce in computer vision language modeling communities for a long time. It's different from designing specialized kernels that work for certain applications, or choosing sophisticated distance metrics. Right? Um, in 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 the era of deep learning, right, we are letting the data speak for itself and learn and get us to the right feature representations. And this entire field of representation learning has its origins back in perceptrons, right? Happened more than 70 years ago. It's one of the initial sparks of the deep learning revolution. And as Vipin mentioned, there has been several winters, several ups and downs in the field of deep learning. But one of the turbocharging moments for representation learning or deep learning in general was this AlexNet winning the ImageNet competition in 2012. And that led to several other developments in powerful predictive architectures like convolution neural networks, recurrent neural networks, solving vision and language problems. Many of these developments, these breakthroughs, were enabled by the availability of massive labeled data, right, that we were able to collect in computer vision through ImageNet, or we could scrape from the internet for language problems. But these advances were still restricted in the confines of labeled data. Right? In applications where you had lots of labeled data, we could see the success of representation learning. All of that changed with this second turbocharger of Gen AI, which is the idea of self-supervised learning, right? Where we are moving outside the confines of labeled data to learn feature representations using ample availability of unlabeled data. So at their very core, these models that are being trained using self-supervised learning are still deploying discriminative or predictive architectures, but they have turned these predictive models on their head to leverage their prediction capabilities, but for tasks that do not need external supervision, right? Or are self-supervised, right? Leading to generative modeling capabilities. Again, this entire field of self-supervised learning has its origins in techniques developed more than 40 years ago. Right? If you go to the framework of autoencoders developed in the 80s, right? We were able to learn feature representations of data without the use of labels. Right? We also had frameworks such as Siamese networks that are exploring contrastive learning formulations. But the turbocharging event for the field of self-supervised learning, as Vipin mentioned, happened with the introduction of word-to-vec, right? Where when we were able to scale these models, right, on the internet scale text data, right, to see very interesting emergent properties appear when we looked at perturbations and transformations in the embedding space. This inspired many developments. For example, in the field of computer vision, right, we had a similar development of masked autoencoders, right, where you could mask a certain portion of the image and see if you can reconstruct that. Right? So there are different frameworks of self-supervised learning, and there is a tutorial link that goes into much more detail about these techniques. But some of these are reconstruction based, where you want to apply techniques like autoencoders or masked autoencoders, or you could explore next word prediction tasks, where given the current tokens, you want to predict the next token. Or you can explore contrastive learning based methods with roots in Siamese networks, right? Where we are exploiting our information of how data points are distributed in the original space, if we have knowledge about their distances, can we use them to learn more meaningful feature representations? Now, notice that all of these techniques in self-supervised learning are exploiting some form of our knowledge of the structure in the data. That they're assuming that in the low-dimensional manifolds, right, there is continuity, there is regularity, right, there is smoothness. Right? And that point is important as we think of the next frontiers of GenAI. Right? What are the other forms of structure, of regularity that we can exploit to develop new self-supervised learning methods? The third turbocharger of GenAI is the framework of building context-sensitive architectures, right? Where the idea is at a high level that to make predictions on a certain point, I need to be aware of the context of the other data points that influence me. Ideas in this space go back to methods like k-nearest neighbors, right? Where you have a notion of your neighborhood or your context, to techniques like geographically weighted regression, Kriging, Gaussian process, and even methods such as Hopfield networks that are modeling interactions between different variables. The modern counterpart of context-sensitive architectures is transformers, right? Where the attentions are capturing the context in a much more flexible way that is completely learned from data rather than using fixed or handcrafted structures of what is the context. For example, what is the right value of k, or what is the right distance function in the original space. Where for every token, for example, if I encounter the word it in a sentence, the model is able to understand what are the other tokens that are relevant to understand pronouns like it. So these are three of the key enablers of GenAI, and we're not going into details about each of these advances. But here is just a landscape of summarizing the different GenAI models that we see in the modern era and how they have their roots in different conceptual areas. We can see that there's a lot of cross-pollination that has happened. Multiple conceptual roots that have come together to create the modern GenAI models. And there are also many untapped opportunities in creating hybrid formulations. Looking at more origins or historical roots to enable next advances. For example, can we combine the idea of autoregressive models with diffusion models, right? Bringing in forward inverse energy-based and autoregressive formulations. So with that, let me summarize with what we discussed. We talked about different GenAI models without going into details of any of them. We talked about their conceptual roots, their history, the backward direction, and the deep learning advances that have enabled them. But what remains to be discussed are the characteristics that differentiate these models, right? In a certain application, when should we choose diffusion over GPTs, and what are their emerging capabilities? And this is where I'll hand it over to Aryan.
Yeah, thanks, Anuj. Good morning, everyone. Welcome to UMN. Yeah, so I'm going to talk about some of these new GenAI methods that you see, what goes into them, what's the recipe, and also what are the new capabilities that are enabled by these methods. So rather than listing them one by one and going through slides, we were thinking maybe we could try to characterize these generative models along different dimensions. And we've listed these 5. And of course, like any list, this is not exhaustive, but we feel it is quite good enough to capture different trade-offs and assumptions that goes behind all these modern generative AI methods or models that we hear about. And also very useful to think about when we are thinking about a new application, for example. So some of them are quite easy to understand. For example, yeah, we care about the quality of our generated samples. What is the fidelity of generated samples? Sometimes it is easy to do that perceptually. Sometimes we can use proxy metrics to do that. We care about suitability to different data types, right? We have data types sometimes which are discrete in nature. Some data type are continuous in nature, different dimensions. We care about the cost of generating samples, right? We'll talk about some applications later where, for example, in digital twin applications, you don't want to wait for your generative model to generate a sample forever. And then there are two very key properties, which I'm going to go in a little bit more detail, which are really very big characteristic. At least the fourth one is a big characteristic of modern Gen AI methods. So one of them is this ability to guide towards desired property, right? All of us here who are interested in some applications are not interested in just unconditional generation. For example, in molecule design or protein design, we're not just interested in generating any protein, but hopefully a useful protein with high activity for something, for a property or high property we care about. So really this characterization, this dimension is trying to ask this question, can we guide these models in an easy manner towards these good specific characteristics that we care about? And can we do that without retraining the generative model again and again as much as possible, right? And so this is really fundamentally having some accessible control knobs during our generation process. And I'm going to characterize the class of model that we talk about today along three categories. So a big class of models, which are the most popular right now, allow high controllability in a plug and play manner where you can plug and play different types of characteristics you care about. Some of them are much harder to control and some of them provide some medium level of controllability. Another dimension along which you can characterize different Gen AI models is their ability to estimate the probability of a sample. This seems probably the most direct thing you would think about when you think about a generative model, but sometimes it is surprisingly not talked about a lot. But this is actually a very useful metric for apples to apples comparison across different types of generative models. So very similar to like when we think about supervised learning or discriminative AI, we talk about accuracy as a metric. Similarly, we can use the likelihood or the probability of samples. So for example, what do you do in standard machine learning? We have a held out set, we compute its accuracy, test set accuracy, and we see how well our model is doing. We can similarly compute the likelihood of a held out set to compare our different models. Unfortunately, I'm here to share the bad news. Not every model provides this uh, probability in a very exact tractable manner. So that's why this is a dimension. And we can also use this dimension, like this property for other downstream tasks like anomaly detection. So the categories along which this dimension we are going to talk about is whether models natively provide us exact tractable likelihood, or we have to somehow approximate the likelihood using some procedure. So along these 5 dimensions, I'm going to talk about the 3 most popular generative AI models that we all hear about today. And starting with GPT, our number 1 model, I guess, where, as Anuj mentioned earlier, so GPTs or generative pre-trained transformers are, it's very nicely captured by this GIF, are autoregressive models, which means they generate sequences by predicting each element one at a time, where each prediction depends on all previously generated elements. And because we typically use transformers as the architectures, here that's why we call them GPTs, but they are underlying the model is the autoregressive model. So this is the characterization of GPTs along the 5 dimensions I talked about. Of course, we all use ChatGPT, so we do know that they provide very high quality samples, at least for natural language or text. The key assumption behind autoregressive models broadly is that they are applicable to data with a particular order in mind. And it turns out natural language, the way we create language, has a particular order, so which is great. Another nice thing about autoregressive models is that they are very nicely generalizable to variable length data. So for example, text is variable length, where typically how we represent an image is fixed size, right? So this is a good property to have of GPTs or autoregressive models generally. Unfortunately, generating samples from GPTs is relatively expensive because you need to generate samples step by step. And the controllability aspect, the fourth dimension, is quite nice because and I'm going to talk about this property in a lot more detail later, but we can literally pass instructions to GPTs and get responses for queries we care about, right? And one very nice thing about them is because of this ability to autoregressively factorize the probability distribution, we get exact tractable likelihoods. And that is why a lot of the time when you read, let's say, papers about language models, there is a metric people always talk about, which is perplexity. Perplexity is very much the likelihood, but turned into numbers, which is easy for us to understand, humans to understand. But perplexity is literally likelihood, and we can get it in exact tractable manner with autoregressive GPT models. The next very popular class of models right now, which is used for lots of domains, going beyond, I think, going beyond language in most domains out there, high dimensional domains, so images, videos, robotics, even lots of scientific domains, are what are called as diffusion models. And the key idea behind diffusion models is that they learn to generate data by trying to reverse this simple noise corruption process. So as you can see in this figure, there's a forward process where we're trying to gradually transform data, real data, into pure noise over many time steps. And the diffusion models, the key magic is in the reverse process where we try to denoise it to go back from noise to pure real data. And the key characteristic, if one message about diffusion model, if you want to remember, is the idea of iterative refinement. So unlike autoregressive models or GPTs, where errors can propagate much easily, here you have a chance because you are denoising over multiple steps. You have a chance to fix your mistakes sometimes. So this notion of iterative refinement is really central to these models, and that's why a lot of excitement along this class of models. And this is the characterization along the 5 dimensions for diffusion models. They provide very high fidelity of samples. And in fact, if some of you might know that the precursor of models in image modeling before diffusion models was GANs. And one big reason was diffusion models actually provided much more high quality samples when you look perceptually at images compared to even GANs. They are natively suitable for fixed length continuous inputs because the notion of denoising makes very natural sense for continuous inputs. Unfortunately, generating samples is again expensive because you're doing this iterative refinement step by step. They are highly controllable, and among the popular class of generative models today, I would say the reason diffusion models are all around us in so many applications is because of their precise controllability in a plug-and-play manner. So any property you care about, for example, just with a frozen pre-trained diffusion, you can just guide it separately without retraining it. And that has become their really, really big deal. And if some of you remember, when DALL-E came out, we were all impressed with images generated by provided text. That really the big deal about that is that you can guide image generation using text, which was not feasible that easy, for example, with GANs or other models earlier. They do not provide exact likelihood, so we have to approximate the likelihood for these models so that we can compare across different classes. So this is the 5 characteristics of diffusion. Another popular class of models is variational autoencoder. And the key idea behind them, as shown in the figure, is that you have 2 networks now where you learn a low-dimensional representation, this latent representation, from your original input by passing it through an encoder neural network. And then a decoder neural network tries to reconstruct the data from this latent input. And typically, this latent input is lower dimensional. So this is a key property of variational autoencoders, which is not there, for example, in diffusion and other models, is that you can convert from high dimensional spaces to low dimensional spaces. So that's why they are very frequently coupled with other class of models. For example, all the video generation models we see out there, Sora and others, use VAEs as the first step to go from the full pixel space of images to a relatively lower dimensional space and do diffusion in that latent space. And these class of models have actually been very popular in the last few years for molecule design problems because this latent space allows you some controllability and you can search in that space as well. And I'm going to talk about those applications later. So this is the characteristics along the 4-5 dimensions that we talked about. VAEs in the standard form have known to be not provide very high quality samples. And they are natively suitable, again, for fixed length continuous inputs. They provide very fast samples because it's just one pass through your decoder. So sampling here will be just passing after you have trained it. You just pick a point in the latent space and pass it through your decoder. So it's much more faster than other two classes. They provide some level of controllability by searching in the latent space. Again, they do not provide exact likelihood, so we have to use approximate procedures to compute this likelihood, this metric, which is very useful. So this is a summary of these GenAI methods, the popular classes at least, along these 5 capabilities. Now, like any list, I mentioned this, and I have to caveat because some of my friends would be working on and coming telling me, hey, but I can use my consistency model to sample a diffusion much more faster. I know about a diffusion language model. Yes, and we are all working on these problems, and this is an active research direction, but I think this is a good starting point, at least to characterize some of these trade-offs when we think about, when we read these papers, we can have these trade-offs in mind to differentiate between different classes which are popping up all the time. Now, as Vipin actually mentioned very nicely in the beginning, these are the classes of models which are very popular. So these are modeling approaches or algorithms. But there is one more key ingredient that goes into modern Gen AI, especially since GPT-3, like 2020, which is this aspect that these models, so these formulations, are also combined with increasingly large amount of data, large sizes of these deep neural networks to represent them, and they are trained on large computing systems. And as shown in this figure, so one aspect of this is that now when you're trying to train these large systems, and you probably take a 6 months or an year investment on training your fastest, so best generative model, you have to be careful about making that investment. So you want to make some observations about how would my performance be. And it turns out this is a very nice property of deep learning models, is that they have very predictable scaling properties, which means as you increase, as you can see in this figure, very famous figure of modern machine learning, if you increase the compute size, data set size, and parameter size, these models, the test performance, which is on the y-axis, tend to improve very predictably, which is very nice to have now, because you can train smaller models to try to see how is, and try to extrapolate these curves. But again, these are empirical observations, and the name laws is always a misnomer, but still, these are very useful for engineering. And some of our systems colleagues will tell us how hard it is to train large-scale distributed systems. So I'm not going to belabor that point. But the one key ingredient that I'm going to talk about a little bit is the data aspect, right? So sometimes people think about it's a very commonly, oh, these models are trained on all the internet. But it's not just the quantity that matters. And a lot of what goes into, there is a lot of amount of effort that goes into curating the right amount of data to train these models. So which means both diversity and quality of the data also matters. So as an example, like this is a very famous PILE data set for language modeling. This is not just, for example, just random text, but also combines different forms, different domains, for example, code and other domains. And the mixture of these domains matter a lot for the final performance of these models. And as an example to show that data quantity alone is not enough, for example, this is a figure from trying to scale up protein language models on just evolutionary sequences where we are already seeing diminishing returns. So which means Either we have to go beyond, maybe to metagenomics data sets and other data sets, or we have to think about other strategies. So data scaling is also a science, and we have to carefully think about that as well. But scaling done well, why we care about scaling is when scaling done well, we have seen examples that it leads to new emergent capabilities for which the model was not explicitly trained on. And this GIF shows very nicely, for example, for Google Palm model, when you increase the data set and the parameters, you get these new properties, new tasks that can be solved, which were not, the model was not explicitly solved, trained for. So really, the general recipe of modern Gen AI is these combinations of new, better algorithms, right, or iterative refinement algorithms, but also thinking very carefully about the right way of scaling these different components. And now let me quickly talk about some of these new capabilities, why we are so excited about them. Of course, the biggest one is that we can generate new instances of high dimensional object, right? Generating images and videos and language, we all use them in everyday life. But for scientific applications, generating proteins, materials, molecules, these are very impactful applications. And these are all high dimensional combinatorial objects, which are much more harder to just search over without these tools, which is really nice. And code, I think this is sort of very nice to emphasize, especially for CS people, that program synthesis is still, I'm not saying it's solved, but is a very hard problem which a lot of people have been trying to solve for a lot of time. But the fact that we can generate code is also a nice thing. The other aspect I sort of alluded it to in the characterization earlier is the plug and play guidance. We can steer these models towards properties we care about. For example, let's say protein models, we can steer towards high activity, let's say an enzyme for some high activity we care about, or molecules for, let's say, a drug property we care about, right? So I think that's another very important capability which is enabled, especially with these diffusion models. So it's much more easier to do compared to the previous generation. And this very nice aspect, which has been alluded multiple times already, is that now we can start thinking about generalizing to novel downstream. So the training is, I've talked about examples, this autoregressive modeling or iterative refinement. Once we train this giant model, I can then use it for lots of different tasks, downstream tasks, in a much more easier, efficient manner. And this is very important for sciences. Why? Because as most of us who's worked with science data sets, we've seen many times that there is a long tail of tasks that we want to solve. And all of them come up with these specialized data sets with their own unique variances. So standard machine learning or AI always had high difficulty solving some of these tasks. But I think this is at least an opportunity with some of these new models we can do that. And of course, one way to do this, there are two popular ways to do it. One way is the standard fine-tuning approach, where you update the parameters of the network, the deep neural network representing your model, with the new data set we care about. But because we talked about emergent capabilities, a very nice property and emergent capability of these models is you can also do without updating. You can also you can also use them for downstream tasks without updating the parameters, or this property of in-context learning. So we sometimes just pass instructions and models reply to us to do certain things, right? Or learning from a few samples. And this is really a key defining aspect of modern generative AI models. And this was actually the popular thing about GPT-3. GPT-3 was just scaled up model from GPT-2, but the big deal was this emergent capability of in-context learning. And this is also the capability, because we keep hearing about agentic AI systems. Agents have been studied in reinforcement learning and robotics forever, but the key capability is that now with in-context learning, we do not have to update our models when we get our observations, and we can use this property to learn on the fly. So that's why it is very important. And this capability, along with the other ones, has led us to the era of foundation models, right? We talk about all these big famous foundation models, Gemini, Cloud, ChatGPT, and lots of other vision language models, for example. And really all of these capabilities enable this modern era. And so just to summarize this part one of the talk, we have talked about the conceptual roots and the frontiers and some what goes into modern Gen AI models. But what we've talked about till now is just about learning passively from observation, learning passively from data sets which is collected. At least I believe, and most people I think would agree, that intelligence and also problem solving there is a very big, another thing we need, which is exploration, active exploration. And that's where comes in reinforcement learning. And Jana Dopa is going to talk about that.